Okay. All right. So I'm going to be talking about basically to continue on from where Aaron left off about speckle imaging. And laser speckle imaging is called many things. There's laser speckle contrast imaging, LASCA, laser speckle contrast analysis. We like three-letter acronyms, so that's why we went with LSI. Not to try to be different. That's just what we called it from the outset. So Bruce Stromberg, he was the former director here. He's now the director of the NIBIB. And this is in a nutshell with speckle. It is extremely simple. Aaron said DCS is simple. This is simpler, not to compete, but it's all related. Is one of the key things here is the physics are related. And so I'll go through some of that. And some of it will be, sometimes it's nice to see things twice, I think. And I'll put maybe a little bit of a different twist on it because we do imaging more. And so, yeah, really simplest, most complicated technology we have. It's statistical optics, probability distributions. There's a lot of faith you have to put in to whether the statistics are actually right in order to be really quantitative with it, but to be qualitative or relative with it, a lot of this you can kind of, I don't say ignore, but you don't have to take into consideration so much. Okay, so the way I'm going to do this is, and I'm not a car person, but I just have some of these I like McLarens, but so I'm going to take a little bit of a different approach to it. I'm going to take the opposite approach to what Aaron did. Aaron talked about applications last and more of the theory first. I'm going to just talk about standard speckle imaging and what you can kind of do with it. Then I'll open up the hood a little bit, and we'll talk a little bit more about speckle theory and how it works. And then we'll talk a little bit about how we can improve its performance through improved measurements and through modeling. And a lot of this work is stuff that it's not necessarily stuff that we did in our lab. We use some of the techniques that have been developed, but the modeling part is something that we've been doing. Okay, so let's talk about first what you can do with speckle. So I'll just kind of start at the beginning of when I first got here. So Stuart Nelson's our medical director here, and his singular focus is treating vascular birthmarks, specifically birthmarks called port wine birthmarks. And so some of the colors are just not going to show well relative to the screen, but I think you get a sense here is that, so the birthmarks, hyperdilated blood vessels, there's some hypotheses in terms of what some of the genetic reasons for the cause, but regardless, they tend to be asymmetrical. Most of them are on the face. And there's been a movement, and I think it makes a lot of sense to try to treat as early as possible. And so here's an example of I don't remember how many times this patient was treated, but going from 3 months to 13 months, much better. You can still see it, but it's much better. And then you get these cases like this where, in this, a child or an adult will get treated. After multiple treatments, there's still a fair amount of the birthmark left. And for the children in particular, they undergo anesthesia. So the Friday surgery day, it's so you hear crying, you'll hear different things going on from the clinic, and it's largely because these children are scared to be having a laser surgery, and you don't want to do repeated anesthesia in any case. So, but unfortunately, that's what's required. And so, just kind of thinking about this in terms of from a tissue optic perspective, treating a port wine birthmark is actually one of the kind of neatest examples of laser surgery. If you're doing something where like LASIK, or you're doing something like where it's ablative and you're basically removing tissue, some of the physics can get complicated, but the basic idea is you want light deposit near the surface and just start raise the temperature up and start cutting away. In the port wine birthmark case, you have the surface layer of melanin, which is melanin's a problem because a lot of the wavelengths they pick are visible wavelengths, so there's a lot of absorption by melanin. But basically, you have to get the light to go through the upper layer to get to these dilated vessels, and the idea is you're trying to cook them. So you deposit the light in a short enough period of time that not a lot of heat escapes during the pulse, and then it gets converted to heat. The energy gets converted to heat energy, thermal energy, and then you get diffusion into the vessel wall, destroy vessels. And the concept here is that you do that, you're successful with that, you then get a good outcome. So the color change goes from dark, kind of darker reddish, purplish to paler. But what's probably happening in a lot of cases, you probably get things where it goes like this, where you deposit the light, you get the heat generated inside the vessel, but maybe it's not good enough. And so you get kind of an incomplete response. And we've shown with like subsequently with a lot of kind of preclinical experiments is that you don't knock out blood flow or you incompletely knock out blood flow, it comes back. The vessels come back. And so the idea here is that you do that and you get basically a poor response. And so one of the things that is kind of is a little bit of the reason why. And thinking about this some going back to here is Stuart and Kristen Kelly, who's the chair of dermatology here, they've treated tens of thousands. They've done tens of thousands of treatment sessions. They're very experienced. But then not everybody has that level of experience. And so with that, how is somebody supposed to know if they actually achieved that or that when they're doing one of these treatments? And so we just thought about this as, how can we measure blood flow directly? And so I saw this paper. This is 2001. This is actually the original. This is basically the key paper in terms of laser speckle contrast neuroimaging. So Andy Dunn, I overlapped with him partially in graduate school, but this is work he did at when Dave Boaz was at the Martino Center, and Andy was an instructor there. So they developed this technique where, and we'll go through a little bit of how it works, but laser, camera, and you can image blood flow. And this was it was a really nice paper that kind of showed a lot of really cool things you can do with speckle for neuroimaging, especially in cases when you have focal cerebral ischemia or you have different neuropathologies. So just to kind of show pictorially first, this is what would happen. So this is data from Christian, who's not here anymore. Basically, you shine a laser onto a rat brain. This is what you see, but you capture an image, and you got all these brain dark spots. We'll talk about a little bit about that, and Aaron already brought some of this up. And then you just run a really simple filter on this. It's just a standard deviation over mean. So you're trying to calculate what's called visibility or contrast in just very small areas. So people typically use 5x5 or 7x7 windows, and they just slide it across, and they calculate this contrast value, standard deviation inside that window over the mean. And this is what you can get. So this is basically saying that in this area right here, there's not a lot of speckle. It's kind of it's a little bit blurrier. Areas like here, for instance, there's a lot of speckle. If I go back here, I mean, it's kind of hard to see on the screen like this, but that's the general principle. Just with that simple transformation, I could give it to all of you this problem, and you should come up with the exact same answer. The edges are a little trickier, but you should come up with this exact same answer in general. Now, what's kind of neat here is that and we'll go through some of the physics of this, is that encoded in there is some metric of motion. So as Aaron said, red blood cells is what we're primarily interested in. If you go longer and longer, you can start imaging motion of other things, but red blood cells and biological tissues is what we're interested in. And then you can do some transformations to then come up with flow maps. Okay. So with DCS, you're looking at one point, kind of one-ish point, really fast, and you're getting a measurement of a flow value. In our case, we're getting a slightly different sort of. We're looking at in this case spatially, just how much speckle is present in that image. So it's a snapshot, and then we can get a measurement of flow. So from a single image, and there's considerations for how you collect that image, but that's the gist of it. And so Yama showed this video. I'm just going to show it again. So this is during a cardiac. This is experiments that. So when Christian was a PhD student, these are experiments that he was doing in Yama's laboratory. This is a cardiac arrest, CPR. So I think he went through it kind of fast. So the idea here is that these baseline conditions, cardiac arrest occurs, and then basically this is Yama literally doing CPR on this rat. No, not breathing, but just chest compressions. And then you get basically this hyperemic response followed by this drop, and then it goes into hypoperfusion. And so Yama mentioned, basically there's all this brain activity, it goes flat lines, and then there's starting to become a little bit more activity. And one thing that Christian kind of showed that was pretty cool, I thought, was that there was two different severities of these cardiac arrests. And just from this information and just looking at here, basically when the blood flow started dropping, there's something predictive about when this occurs and when this bursting actually comes back. So it's kind of, and it was you can create a predictive model off of it. And the exact reason why, we don't know. We had some hypotheses for why it might be, but it's basically just kind of shows, just with these blood flow measurements, laser camera, imaging, there's some interesting information you can get. And all these techniques I'm talking about at the beginning, for the most part, the processing is pretty much all the same. And it's just what twists and tricks can you do with it? So this is basically looking at it from basically going back to the poor wine birthmark. So this is actually some, this is work that was from 2009, 2010. So what were you all at that point? I didn't want to know the answer. But this is actually, this is actually a GPU accelerated system. So it was before, we were using CUDA before there was any documentation about it. Something David Kuchar actually suggested to us is, hey, why don't you try doing a GPU calculation? Because it's a very repetitive calculation you're doing across the image. So you can massively parallelize it. So Owen Yang is, you tell him that he can't do something, and he figures out a way to do it. That was kind of the mantra in our lab. So I said, there's no way you can do this. And he didn't know C, he didn't know CUDA, he didn't know any of that. He figured it all out. And so we were able to get a GPU accelerated imaging system for looking at blood flow. And we took this into the clinic. And so this is just a video that's going to show, in all its ugliness, and there's nothing that's been like, you're going to see like the surgeon's hand in the picture and everything. So, and we had a webcam attached to this. So basically you can see that during this treatment, you can see the hyperperfusion in that area, and you can see with the laser treatment how it's going away. Obviously, we can't see through the hand, but the basic idea here is that, so you're going to see some areas that look like they still have some perfusion. So the idea would be, should the clinician retreat those areas right on the spot? They don't have this sort of information, obviously, in a normal treatment. So, and we show some correlations that reduction in flow does seem to correlate pretty well with the reduction in the color. So as an example, this is one of the first things that we're pretty excited about this. And just to kind of show, you could also do it like if you're treating with so Dr. Nelson in this case used one laser to try to treat. So this goes a little bit deeper, 755. It's not a standard wavelength for treating the vasculature, but he used that first, and that's what he saw. And then basically switch to a more conventional laser, and then you can start seeing the additional reduction. None of this is image guided. This is us passively watching. But it just kind of shows you what is possible with a technique like this. This is work from Andy Dunn's group. Lisa Richards was a PhD student with him. And this is obviously more, it's basically taking speckle and just putting it into a surgical microscope in this case for doing neurosurgery. And they have a camera basically attached to one of the ports on the head of the system, but it's just, you need a way to get the laser light there, and then you have the camera, and then the processing's all just that standard deviation over mean calculation. So these are the sorts of images you get. Obviously, there's a color image, there's a speckle image, or a flow image, and then there's basically them superimposed on top. And so, this is, I know Andy and David Miller have created a company with this. I'm not sure exactly where they're at right now, but it's really, really promising, I think, for neurosurgery. These are commercial devices, just to kind of show you what exists. And so, you have the laser, you have basically the camera and the laser built into there or into that part over there, and that's really it. I mean, the processing's, they come up with slightly different values. We've done direct comparisons, and the values are slightly different. So we're not sure exactly what processing they use, but very similar. So this is just an example of using this is one of the Moore systems for an esophagectomy. So this is the case. I'd seen one of these surgeries, and it kind of blew me away. Basically, if you have a section of the esophagus that you need to resect for whatever reason, there's a cancerous lesion, they will, they'll cut off that region, and they basically pull the stomach into the abdomen, and they basically reconnect. yeah, it's kind of a crazy thing to watch. And so this is just an example of, this basically showing, this is the stomach, and then these are just images after. But the system is, yeah, it's just that laser and that camera. One thing we've been working on is trying to just create handle type systems and get them into places that are more difficult that when we can't wheel in a bigger system. This was our brute force solution, just attach the system to a Microsoft Surface and let somebody walk around with it. And of course, we're stupid. We used a big metal block to attach it, so it's kind of heavy. It stabilized. It was kind of it was but then you take some tricks from Hollywood with some of these stabilized systems, and that's motion stabilized with the gimbal and everything. So you can make them pretty small and pretty accessible. This is an example of that first system on the left. This is an example of a neonate that we imaged that had compromised blood flow to the thumb, and so we were able to actually see that in our images. So that Mustafa Kabir is at the Children's Hospital here. He's a pediatric surgeon. So just and there's a lot of, if you just look up laser speckle contrast or laser speckle blood flow, just look at the list of papers, there's a lot of different applications of the technology of either really simple lab systems or a lot of these commercial systems. So, you can go with that sort of system. We're talking 50K, a little bit more. You can go with a system like this. If you don't have the money and you just want to duct tape things together and get them to work, you can get webcam and a laser pointer. The webcam's got a little caveat to it, but you need kind of specific ones, but you need to take filters out. But basically, you can do this with a webcam and a laser pointer. This is work from Andy Dunn's group as well. We've done something similar. Yeah, it works. Is the quality of the data good enough for routine use for serious applications? Maybe not, but it can give you data it can give you data. It's a great demo system for like high school students and nothing else. And our systems are definitely on the lower end. Kiki, how much does your system cost? No, it's better than that. But it's low, but it's pretty low. Yeah, 150, yeah. And so yeah, we built ones for hundreds of dollars. The ones you're gonna see are they're good systems, but they're also, I don't know, maybe $3,000, and the laser's the main part of that. You can also take kind of a standard type of like a performing thing, so Honda Civic, but then you can soup it up. In this case, this is a 306 horsepower Honda Civic. So you can take the pulse oximeter sort of concept, and then you can add flow to it. And this is where Michelle Kine, when she was talking about 10xing this stuff, this is the sort of thing that is it really is signal to noise we think is a 40x, but basically this is nothing more than speckle just put into a pulse oximetry shape. And so Sean White, I'm not going to talk much about this. Sean White he's speaking tomorrow at dinner, so he could talk about his whole journey with the startup. Okay, any questions so far? Now we're going to dive into a little bit of where this all comes from. So there's going to be a lot of equations that come up here, and I want this to be intuitive. So I'm just going to point out the parts of the equation. And actually, Aaron helped out by talking a lot about the correlation diffusion equation, which I'll touch on a little bit later. But I really want to start kind of this concept of contrast, and I want to build intuition. Now, this is the reason why I'm doing this is because the system is very easy to set up and to take measurements. Why it does what it, where the actual origin of the contrast and the signals are is something that a lot of people don't have to think about. And so I just want to kind of give a sense of that. So I'll spend a little bit of time talking about this, and then you'll probably wish I hadn't. So Joseph Goodman is really, I mentioned Arjun Yoda was really the pioneer and kind of the godfather of correlation spectroscopies, of that sort of technology, that line of technologies. Joe Goodman really is that for Speckle. Start with radar, but it's really, a lot of the laser-based stuff has really been adapted from him. Those books, like they took me several times to kind of start appreciating what's actually in there. I haven't gotten through a lot. There's still a lot of it I haven't gone through yet, but there's a lot of really interesting information in there. In terms of the actual kind of first speckle contrast, or what I think is the first speckle contrast paper, it's one from 1981, where they actually did retinal imaging to try to look at blood flow in the retina. But this is there was no such thing as a digital camera back then for scientific use. So this is literally set up a system and set up the optics so you can they take a picture on film, develop it, but with the optical setup that they had and the filters they had in place was the idea of trying to actually image a speckle contrast or get a speckle contrast image directly on the film. So definitely not real time, but it was pretty cool that they were actually able to do that. So this is something that Boston had shared. So this is, we're talking about just electric field here. Okay. We will ignore the magnetic field. And then you have the wavelength. So we have amplitude and phase here. And so let's just go through. So electric fields, we have the real part and the imaginary part because we have the amplitude and we have the phase. Okay. And so if you just basically at each pixel, and actually one thing I should say, and Gwen will be proud of me for saying this, is some of the snippets of code that I use to generate some of these images are actually they're using generative AI. So she'll be proud of me for saying that. So this is basically just if I just sampled the real and imaginary parts at each pixel from a distribution, and then so they're independent, and then just plotted them. This is and plotted them as an electric field. This is what you would see. Or that's intensity pattern, actually. So you already see kind of the speckly type pattern. Now, this is really, really, really synthetic. And it's not quite what we see when we image, but this kind of gives a sense of already be able to generate something that looks like a speckle pattern. Okay. So we send laser light in. And one way of thinking about it is that each interaction, as the field's going in, each interaction the field has with the scatterer, we were talking a little bit about this, is that scattering is not just bouncing off of things. It's actually you're exciting a dipole and the dipole re-radiates. So if you just kind of think about that as you're sending all this light in, and in each of these interactions, you're creating a new wave that comes out. Okay? Just so one big wave, one big coherent in-phase wave basically creates all these little waves with each interaction. It could be moving, it could be not, it could be a moving scatterer, or it could be a fixed scatterer. So what's going to happen is that's going to happen, and as the light that you detect coming back, it's all going to have traveled different path lengths. So one way of thinking about this is, okay, here's our wave right here. Let's just say that we have a camera here, and this camera basically goes, it basically 4 is the maximum value you can get here. Okay, so the amplitude of this wave is 1. Okay, and we're just going to look at 3 of these pixels. So if they're all aligned, so they're all in phase, and they all hit this point right here, then you're going to have basically they're all constructively interfering perfectly. You're going to get and each one's got an amplitude of 1, so you got an amplitude of 4. Okay, so you get a bright, and then we'll just call that our bright spot. If we just start shifting the phase of these relative to each other, so in this case, this one is perfectly destructively interfering. These two are perfectly destructively interfering. So 0 plus 0 is going to be 0. So you're going to get at that green location, the 0. And if you just shift a few of them a little bit, then you have maximum value there. You have something a little bit lower here, something a little bit lower than the max here, and then you get a 0 here, or close to 0, or close to negative, sorry. Then -1, then you're going to get something in between. So we have our bright spot, our dark spot, and something in between. And this is really the heart of it, is that you have all these phase shifts going on because of all these different path lengths. One way to think about it, and they're all hitting each pixel of your camera. They're all going to have different contributions. Some are going to be very constructively interfering. Some are going to be very destructively interfering. A lot of them are going to be in between. Okay. Oh yeah, and if I just kind of shift, actually, I don't even know what I was trying to say there. Never mind. What am I saying here? Why am I moving those? I don't remember what I was trying to say there. Um, but yeah, so basically you get all these different path lengths, so you get all these different phases, relative phases, and then you get this phase, you get all these these changes in phase. And one of the assumptions with Speckle is that if you were to basically look at basically the phase shift itself, it's a random distribution between 0 and 2 pi. So equal opportunity to get any different phase shift. And if we look at, so with the overall electric field going in, if we just look at each of the partial fields, so each partial field is going to be a complex number, or a complex field. So you have the amplitude, you have the phase. So just like I showed at the beginning, the electric field is a complex quantity. And then if we just sum them all up, then it's just kind of simply we have the electric field, and then we have a real component, and we have an imaginary component. With an overall amplitude, we have kind of an overall phase for each of the partial waves. And if you do a lot of these, you can basically then come up with each of the real imaginary parts. They can be sampled from a Gaussian distribution that's zero mean. Okay, so you can start just take once again if you just kind of simulate this, you can start sampling, pulling out real and imaginary values from each distribution, and they basically are what's called circular complex Gaussian variables. So why is it called that? This is what it actually looks like if you take all those different real and imaginary parts and you plot them against each other, as you end up getting something that's a circular distribution. That's why it's called circular Gaussian. So these are all the assumptions that a Speckle field, what's called a fully developed Speckle field is based on, is that it follows it follows this sort of distribution in terms of the real imaginary parts. The phase is distributed equally between 0 and 2 pi for all the different components. And as Aaron alluded to, we don't measure electric fields in general. We measure intensity. And so if all those assumptions come into play, then the intensity actually will follow an exponential distribution. And so this is, if I took an image that I generated using, basically with these values right here, and I just plot the intensities. And this is basically the distribution. So most of the pixels are darker, and I have some brighter ones, but it follows this distribution. This is a perfect Speckle pattern. We don't measure perfect Speckle patterns, but this is just at the theoretical level what is going on. So yeah, so fully developed an instantaneous Speckle pattern. We don't measure instantaneously either. DCS is getting a lot closer to measuring instantaneously, but we have a finite time over which we collect data. Otherwise, we don't get light. We don't get any signals. So if you go past the instantaneous part and just kind of a simple experiment. So if we just take one of those instantaneous realizations of the pattern, and then we just generate a whole bunch of them. And then we just average them. So that's kind of almost like you're saying, okay, here's one image. Over time, I'm just stacking a bunch of other newly generated images. What happens to the pattern if I just average it? And so here's one image. So this is the perfect image, contrast of 1. And then if I just start averaging, so this is not exactly following any physics per se. This is just kind of showing it as an example. As the Speckle pattern starts changing with time, you're just going to get, you just expose longer and longer. You just are able to visualize the Speckle less and less. And that makes, I think, some sense, because it's almost like, even if something's really slowly varying, so let's just say I put a turtle down here, okay? And if I just took a snapshot of that turtle and I kept taking snapshots of that turtle, and I then at a correlation between those images, probably going to be a pretty high correlation. But if I do this for a day, and I just keep taking pictures, assuming the turtle's probably going to move. And so over time, if I just average that, I'm going to just see where that turtle is. It's going to look a little bit blurry. And just the features of that turtle, because the turtle's moved slowly, but it has moved. And so it makes sense that you have an exposure and you make it slightly longer and longer and longer. you're just going to start losing your ability to see speckle. Okay. And then if you look at the intensity distribution, so this is where the fully developed part starts breaking down. This is what you would see for that one image. And then you start going to more and more images averaged together, you start really violating this sort of exponential distribution. So a lot of things start, I don't think they start breaking down, but there's a bit of a disconnect between what's a perfect theoretical speckle pattern versus what actually starts happening in practice. Dad joke. So when I was younger, I was obsessed with the difference between sine and cosine. As I got older, I realized it's just a phase. Yes. All right. Moving on. So this is the contrast value. So this is that standard deviation over that mean. And so this is the relationship actually that can be developed basically to explain the spatial contrast with something that happens in time at one point. And so we're gonna break this thing down here. So we measure this. T is just our exposure time. This is just an average intensity. And then we have, so exposure time we're ultimately trying to get to this value, some specific time value. So Aaron talked about it with the correlation, with the autocorrelation function. You can look at certain values of that autocorrelation function, and you get some characteristic time out of it. So it's called a decorrelation time. All right, so let's go through this. So this C term here is the temporal autocovariance. So what it's doing is it's basically if you think about the DCS signal for a second, if you measure the intensity at a point, you have time here and then you have some delay time here, and that delay time can be different values. But basically, I'm just looking at how similar is the intensity here to here. I'm sliding this across my image, across my signal. And then I'm doing it something shorter, and then sliding it across the signal, and then something shorter, and then something shorter, et cetera, et cetera. Okay? So we just kind of go through really simple extreme examples. So if my intensity is a constant, so from here to here, it's obviously it's a perfect correlation. Here to here is a perfect correlation. Here to here is a perfect correlation. So in this case, the covariance value is actually a 0. And if I just go through the math really simply, then I have no speckle pattern there. It's just basically the speckle is not. It's not changed. It's basically there's no. It's a flat line. There's no dynamics there. If I see something that looks like this is a little bit closer to what Aaron was showing. I guess showing it below. Probably should have put that below. You don't measure negative intensities, but basically, this is intensity over time, and you just see these fluctuations. And so, thinking about this some more. So we have an average intensity value. We have time plus some delay, and we can start moving that thing around, and we start calculating covariance. Okay, so we do this for, as I was saying, for all delay times between 0 and the exposure time t, and then we integrate to get a speckle contrast squared. So here's 2 example waveforms that one can measure. These are actually simulated. These are things simulated a long time ago, but just kind of just showing two signals you can measure. And so, first question for you. So if I calculate the temporal autocovariance, I get these 2 curves here. So which curve corresponds to something that's faster varying? You can just look from 0 on. They may have it's A or B. So I'll give you a second, and then I'm going to poll you. All right. Who thinks it's A? Who thinks it's B? Who thinks it's A? Who thinks it's B? All right. It's actually, so this is basically, so this is a covariance, so basically, when the covariance drops more quickly, actually that's corresponding to a higher degree of motion. Okay, it's getting less similar than itself faster. So if I make that time, so the same thing. It's like if I took a snapshot of that turtle at time 0 and then time tau. If it's a short, if that time over which that turtle looks the same is shorter, that means it's moving faster. Okay, so this covariance function actually drops quickly, and just from the math, you get a lower speckle contrast. If you integrate underneath this curve, same thing over there. It looks more similar to itself longer. So then it's basically a slower decay. And once again, if I integrate underneath that curve, I can get a higher value of speckle contrast. So faster motion, slower motion. Okay. Aaron brought this part up. Basically this is looking at intensity. And you can basically derive from that equation, you can basically put it in terms of covariance. And so you get the covariance as a function of the mean ensemble average of the intensity squared times the intensity autocorrelation function minus 1. Okay, so there's a relationship now between the covariance and the autocorrelation function. And as Aaron has shown, we measured with the different intensities, you can basically then get this G2, that's the intensity autocorrelation function, as a function of G1, which is the electric field function. So we had covariance. We basically went, and now we started with covariance back here, no, actually back up there, and now we're putting it in terms of G2 and G1. And the reason why we do this is G1 we think we have a better handle on. So for Brownian motion, which Aaron alluded to, you basically have a single exponential decay here. And so this time here is what's called the decorrelation time or correlation time. This is basically saying, if I look at one point of my image and I look at it over some time, how long does it take for that point to kind of not look like itself anymore? So it's a decorrelation concept there. And so this is a characteristic time, this tau sub c, that kind of says how long a speckle is present. So the longer it's there, that means that things are probably moving kind of slowly. The shorter time it's there, that means things are probably moving pretty quickly. Now, it's not this simple. G1 can really take on a lot of different forms. This is the one we just most people kind of stick with. Sometimes it's a superposition of these. These are actually these two papers do a pretty good job of talking about it. It could be a square of this, it could be a square root. But it's some kind of it's related to this general form here for G1. But if we just assume this, and once again, this is probably the most common assumption that's made, we then, basically going through, we ultimately replace the covariance term with this G1 squared. And that we can then do a pretty simple integration to get contrast, which we measure, exposure time, which we know, and the only unknown here then is correlation time. There's that beta term. The beta term is basically it's an instrument response, and there's lots of discussions on how you can measure that and what you can do with that, but we'll ignore it for right now. But you measure contrast, you can get correlation time out. And this is just one single spatial map that you're measuring. So let's just look at this now. I just plotted correlation time over exposure time. So if we say exposure time is a constant, you could just assume this is a correlation time, okay? So contrast versus correlation time. And this is the sort of curve you got. So it's a semi-log plot here. So first question I'll ask is, okay, let's just say this, this is the relationship between some measure of dynamics and contrast. Where should you operate in this curve and why? So we got A, B, C, D, and E. Who thinks it's A? B, C, D, E, F. No. All right. Well, so the basic idea here is this is the thing that you're measuring, right? So this to some extent defines the dynamic range of your measurement, and you're relaying that dynamic range of your measurement to the dynamics here. And so this probably is a pretty good place to be able to be measuring, because you're able to see large range of correlation times for a given range of contrast.
But you want high contrast, right?
You want higher contrast, but you also want dynamic range, right? So if I were working at 1, that's a great question. If I work at 0.9 or 1, basically very small changes in contrast very small changes in contrast have very large impact on the correlation time you measure. So
Is this like the time that is the bottom, the time delay?
this would be, yeah, this is correlation time divided by the exposure time. So if we just assume a single exposure time, that's correlation time. So this gives you basically two orders of magnitude here and this is what you're measuring here. So you have a large dynamic range here. I could see why you might pick up there, but this gives you a large possible range of contrast that you can measure from your image that map onto 2 decades of correlation time values. So in this case, this is 0.05. Sometimes it's also, you kind of have to know a little bit about the dynamics. One thing I didn't say, which is kind of unfair, know a little bit about the dynamics of what you're trying to measure. So that's basically, these are the 2 values of correlation time over exposure time there. These are the contrast values that would be associated with it. So a pretty large range of contrast values. So you can tune the exposure time. If you have some sense of what the dynamics of your system are, you can then pick an exposure time to try to get you mapping into this range here of contrast. Now, there have been several studies on this that kind of empirically looked at this for flow values in like the brain and the 1 to 5 millisecond range in terms of those roughly correspond to 1 to 5 milliseconds in terms of the actual correlation times you're trying to estimate. Sometimes you're trying to go much shorter than that as well. So you can pick an exposure time to basically try to match the dynamics of your system. All right. Let's just say that this is where we're at. So if we want to be more sensitive to faster flow speeds, let's just say that this is where we're working, and then now we think our flow speeds are faster than this. Do we want to increase the exposure time or decrease the exposure time? Want to see faster dynamics? Decrease. So decreasing the exposure time would obviously decrease this, which would then basically, it pushes us more into this direction right here. But also intuitively, you can just think about it, right? If you're trying to take a picture of somebody running, you want a fast shutter time versus somebody that's just walking. If we increase the exposure time by a lot, what happens to the contrast? It decreases. And this goes back to my example of if you just image something for a long enough period of time, your speckle pattern is just going to completely disappear, right? Things are moving in your area, blood's moving faster, but over time, you have cellular motion. So you basically have just these other changes that are occurring at the different points that are moving at very slow speeds. But you make your exposure time longer and longer and longer, you're going to start picking up those dynamics as well. And eventually your speckle is just going to disappear. Let's skip that. Okay. So this is just kind of just showing, if you pick these exposure times, just kind of showing what sort of contrast values or what sort of contrast values you pick up. So, and this is where, like going through the kind of this theory here, single exposure speckle works really well for a lot of things. So looking at relative changes, for instance, you can pick up these relative changes that occur. There have been several studies that have looked at, is it a linear response or not? And some of them have big asterisks next to them, but you can define like a linear response range of your system as well. So like 10 milliseconds seems pretty good for exposure time, seems pretty good for roughly 1 to 5 millisecond or 0 to 5 millimeters per second of flow if you use a phantom. But it's not perfect representation, but it gives you an order of magnitude. One of the cool things is that Julio Ramirez San Juan was he was a postdoc here, and he's a researcher in Puebla, Mexico, and at Inahue. So we work together on and off. But if you kind of go through if you go through the math and you start looking at just fits the portions of the data for a contrast value of 0.7 or lower, which is a lot of cases what you actually have, you can really go to a very simple equation here. So that equation is about as simple as you can get in terms of coding and in terms of just calculating. You have exposure time. The two is extraneous. You have exposure time, measure contrast, correlation time. You can calculate like that. And once again, it works pretty well for a lot of applications. How big is a speckle? I guess this is one of those things that, so we have the electric field here. And this is the image I showed before of the speckle. This is not what a speckle would look like if you imaged it. Okay, this is like absolutely perfect. This would be kind of like if you knew this. This is what it would be if you knew it, what the field might look like. But when we image speckle, we suffer from the same limitations of any other imaging modalities, diffraction limited. So we can't image at the nanometer scale with the camera with a macro lens on it. We're restricted to basically the Bessel function of that. We typically have a circular aperture, so we have a Bessel function for that in terms of in terms of what we can focus down to, the smallest spot. So this is very similar. If you look at microscopy, you're going to see very similar sorts of equations. So if we know the f-stop of our system, the focal length over the diameter, we know the magnification, which you can determine either optically or empirically. And obviously we know the wavelength, or we should know the wavelength. You can then get a sense of what your minimum possible speckle size is. And so this is simulation, but basically this is just showing that if you make the aperture bigger and bigger, the diameter of the aperture is getting bigger, so then the F number is getting smaller. Basically your speckles get smaller and smaller. So you would think you want really small speckles. That sounds great. Because this is basically your minimum resolvable spot. So, we have bigger and bigger diameters. So basically the numerical aperture of the optics of the imaging system is changing. And so you're basically getting higher and higher spatial frequencies then. So next question. Imagine this is your detector. And you know the size of these pixels and things like that. You do this calculation, and this is what you kind of see. So you either have speckles that are small compared to the pixel, or you have speckles that are big. What's better? Smaller, why?
So you can detect as many, you have finer details, right? Or, okay, if you have large speckle, you're limited by the detector in this case, but in that
Yes.
case, yeah, okay.
Yeah, so no, you brought both, those are both good points. You would think smaller, but the thing here is that you have all these bright and dark spots, right? So if your speckles are about this size and you bright dark, it's going to average out. So you're actually losing your ability to see the speckle contrast. Versus here, this is worse from a resolution standpoint, but it's actually a really bad drawing. They shouldn't be touching, or they should be overlapping. But basically, you have a better chance of being able to sample each individual speckle itself properly. You're getting closer to that. And there have been some studies that have shown basically it's a Nyquist sampling concept. This works. This is one of those things that we've had a lot of discussions on. Sometimes this works pretty well for us, and sometimes like empirically, sometimes it doesn't work for us. And we've really been trying to figure out why. But this is the kind of the rule of thumb: is you want basically 2 pixels per speckle. For DCS, you want 1 speckle per pixel. And so the way we calculate it, so just going back to this standard deviation over mean, this is a 5 by 5 window. We'll calculate standard deviation over mean in this area. Just move it over, calculate, and there are a lot of tricks to doing this, but you can basically calculate speckle contrast at each one of those points. You put the speckle contrast into a new image. Voila, you have your contrast image. Okay. Any questions on this so far? So we talked about if you're going to do a set up a speckle system, you have a camera, you have a lens, you have a laser. So we talked a little bit about what's going on in terms of the physics of the speckle pattern, but practically speaking, you have an exposure time that you dial into the camera. You know your pixel sizes, you know the magnification of your system. You can maybe change the f-stop on it, depending on the lens. You can then calculate what the speckle size is based off of those optics. It's strictly based off the optics and the wavelength of light. And you can try to set everything so that you're sampling the pattern properly. And you're ready to go. Yeah, Brenda.
So back to the exposure time, you said if you increase the exposure time, that would decrease the contrast. But like, don't you need to increase the exposure time sometimes to be able to see certain
Yes,
components of?
absolutely. If you don't have so the simple answer would be get more light in there, but that's definitely not always the answer you can do, especially with some of these other tricks. Actually, Kiki and we're having this discussion with some people in my lab. You can, and actually, no, well, you can go to pretty low levels of average intensity in your image, and you still can get contrast that if you double the light, triple the light, you get similar contrast values. So the first thing I'll say is you can work in pretty low light level areas, depending on your camera, right? If you have and your laser. If you have a unstable laser, if you have a camera that's got a lot of noise, that noise floor or the minimum goes up. But with we call it the Creuset limit after Christian, but with some experiments we were doing where we had really short exposure times on a 8-bit camera, so 0 to 255, you can work at an average value about 10 and still get data. Actually, if you work too high of a value, you start hitting saturation limits on some of the pixels, and that's actually worse. Yeah, but at some point you're going to reach an exposure time. You're going to reach a conundrum where you can't, and that's if your exposure time still doesn't allow you to get enough light, then you might have to rethink the experiment, to be perfectly honest.
I've noticed sometimes where I have like an RGB and our camera taking an image, and as I increase the exposure, it looks more grainy. Is that grainy aspect having to do with the speckle?
This is with the laser, as the lasers, or this is
just like a broadband.
You shouldn't. Then you shouldn't see any interference from you shouldn't see the speckle pattern then. So that would be if you're going to too low of intensity, or too increasing. That's like maybe there's some nonlinearity in the camera, or there's I don't know at that point, but that won't be an interference pattern at that point. Any other questions? Okay. This is what we kind of generally assume, and so this is, we have this area that we're imaging. Let's just say this area is the entire volume that we're imaging, or we're collecting data from. Homogeneous medium, and basically Brownian motion is dominating. Let's just say everything's moving due to Brownian motion. So this is the basic assumption that's brought into play with standard speckle imaging. This is what we're assuming. Obviously, it's not the same thing as tissue. This is probably going to be closer, at least for skin, this is going to be a lot closer. But for a lot of other, if you're imaging through the skull, you're imaging through areas where there's flow, but then above it, maybe there's a lot less flow, or there's no flow. This is going to be a more similar, or this is going to be some situation that you encounter. So same thing, we got the homogeneous mixture of particles, Brownian motion. All we do is just buried this, or we put a layer directly on top of it. That's all we're doing here. And we get a different correlation time. And so, basically, we kind of have these moving scatterers that we're trying to measure. And we call them dynamic scatterers. The dynamic scattering thing, you can kind of get lost in terms of what constitutes a dynamic scatterer. If you have a photon going through 40 scattering events, hits a red blood cell once and scatters out, is it dynamic or is that static? If it doesn't hit a dynamic scatterer, and all scatterers are moving in reality, everything above absolute zero is moving. It's just you're kind of making these assumptions here that the things you're interested in that are moving, dynamic. The other things, if they're moving much slower, they're static. And so going back to this, we kind of have this sort of case here where the red is dynamic and the cyan is static. Okay? And then it gets more complicated because now your electric field is not just as simple as that the real and imaginary parts. Now you have part that's the real and imaginary parts due to the fluctuating component, the dynamic component, and the static component. Okay. So we're just talking about this. We have our G2, nice equation. G1 is a nice equation. We can put it into contrast and we can get a nice equation. And we can get a really nice equation if we make that assumption. So this world is the one we want to live in, ideally. But when we deal with that sort of scenario, we can throw it all out the window. You can still use it. But and a lot of, when we image skin, we still use basically make this, we know that it's not a perfect model. This is what your G2 actually turns into. So this was all derived by, so this is Ashwin Parthasarathi and Andy, who at that time was a graduate student with Andy Dunn. And so you get a much more complicated G2 equation. It's not G2 equals 1 plus beta G1. Now you have these other terms. The nice thing to know is if you do a sanity check, oh, sorry, I'll get to the sanity check in a second. So we look at different ways to try to overcome the fact that this is more complicated now. We have a static layer on top. So one way to do it, the simplest way to do it, so we, in general, take a single image, we slide this window across, we get our speckle contrast map. And if we want to reduce noise, we can do that for a sequence of images and then average it all out. Or you can look at each pixel over time. So this is a very, very, very poor man's DCS. It's not even DCS. But the concept is that you have these short bursts of exposure times where you're exposing over this, while this thing's fluctuating like that, you're just capturing it every so often. Okay? And so you look at each pixel now at the intensity over time. So instead of looking at a spatial window, now you have a temporal window at each pixel. And so the first paper was about, over 20 years ago. The idea here is that if you're just looking, if this baseline, you're just looking at kind of fluctuations of that intensity around that baseline, that's a little bit less sensitive to, or it's a little bit less sensitive to just the quote unquote stationary components inside the tissue. So how can we show this? So we just do a flow phantom. So we have a pump, glass tube here, PDMS block. So there's some work we did with Julio, laser camera. And so we just have basically this layer on top. And we change the flow speed. We're just flowing intralipid in this case. You can use blood, you can use whatever your favorite scattering medium is. So if I just vary that top layer thickness for a given flow speed, and I just change exposure time, but if we just look at a single exposure time, basically, as I change the speed, and I put more and more top layers on top of it, basically you start seeing this difference in terms of the flow that you measure or the contrast that you measure. So that's not good. That's already showing that same speed, different amounts of absorbers on top or scatterers on top, it's not measuring the same thing. If I do temporal instead, this is what I'm able to see. So basically for a given exposure time, it's much less sensitive to that overlying layer. Okay? So temporal it's a simple trick that you can do. The downside, you need to take more images. So it's got to be stable over that time. Like if my thing's moving like this, so kind of slowly, Spatial works great because each image is snap, 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 snap. So I could still get images and I could get measurements of the dynamics that occur because each one of those images is taken such a short period of time. If I'm doing temporal and I'm moving like this, well, that one pixel is moving now. So unless you can keep track of where that one pixel is, you basically can't do temporal anymore. So it's got to be very stable. But you can overcome that scattering layer on top if you can do it. I don't know why I put the car there. So going back to this, going back to this a function here, the more complicated function. If we do some sanity checks on this, we assume everything's dynamic. So this goes back to the previous simple LSI. We just plug in rho equal to 1. So rho's, and I think Aaron used alpha, basically the fraction of moving scatterers. So we just assume everything's moving. So that gives us that G1 that's a negative exponential. We get basically back to the secret relation. So works this sanity check 1, it works great. If we assume that nothing's moving, we basically will get G2 to be a constant. Just plug and chug. And so it does reduce back down to expected trends in terms of the data. So you stress test this equation, it seems to pass some of the stress tests. Contrast, more complicated too. This is all assuming that exponential decay for G1. So we measure contrast and we know our exposure time, but there's a lot of unknowns here. There's that beta, there's the noise term, there's a correlation time we want to measure this. There's that fraction of dynamic scatterers, and there's this instrument function. So what we do is, in this case, there's 4 unknowns. So what we just do is we just image at more exposure times. So we try to build this curve up actually. And if we can build this curve up, we can start extracting out other parameters. So simple, pretty simple. There's elegant ways to try to do the multiple exposures. Andy's group's done a lot of that. There's very brute force ways. I could just sit there and just change the exposure time on my camera, grab another image, change the exposure time, grab another image. I could do it that simply. Some caveats there. The elegant way is you have a single exposure time and you change the amount of light going in, the effective exposure time by basically redirecting the beam. And so we do a flow pattern experiment. So in this case, we measure contrast at different exposure times. We get something that looks like this is real experimental data. This is from our group. So you basically got this trend that looks like that. So you go to longer and longer exposure times, contrast goes down, right? They start blurring out. And you can fit to that using that equation. And then you can start doing this for a lot of different flow speeds, and you get a different characteristic curve for each one of those flow speeds. So which one do you think is for flow speed of 0? And which one do you think is, so 0, this was 0 to 10 millimeters per second. Which one do you think is 0 and which one do you think is 10? 0 would be higher contrast or lower contrast? Higher. For no flow, your speckle pattern is more static, right? So which one do you think is the 0? Blue line. Yes. So basically, this is just increasing flow speed that way. So it's a way to basically be able to back out. You have to do more measurements, but it's a way to be able to back out, even with static, these quote unquote static components in your object or whatever you're imaging. You can try to account for that and back out an accurate measure of the correlation time. And just to kind of show, if we then measure 1 over the correlation time, which is our flow value, these are the real flow speeds, works pretty well. So this is actually without the top layer, and then if we put a top layer on top, works pretty well. It breaks down eventually, but in terms of the thickness, but 200 microns, at least for skin, that's a pretty thick epidermis, and so it gives you a sense of what you can kind of do. Yeah, Kiki.
Say that, I know this is, but when you're doing the multi-exposure, are you adding are you using that?
We are not. We are doing, so the simplest way would be go back to here. So there are 2, 4, 6, 8, 10. There's 16 exposure times here. You could do the adding frame part. So in this case, but you're also adding the noise. So in this case, this one I believe, this data I believe is we had a single long exposure time. So we did it this way that Andy Dunn's group does it. We had a long exposure time, and then for the short exposure times, basically we had an acousto-optic modulator that would deflect the light. So either deflect it really short period of time or really long period of time, and would change the intensity with each of those flashes. But yeah, you can do it. You can, yeah, like I said, the simplest way would be, simplest way, but it would be a pain, would be you capture at the short exposure time, stop the camera, change it, et cetera, 16 times. Or you could do, I think what you're alluding to is you can basically get a lot of short exposure time images, and then you can start just digitally integrating them. So if you get one of these images, and let's say there's twice the exposure time, you just get this image, or you would, if this were 2 images, you would basically take 2 consecutive images, integrate them, and then you get one longer exposure image, et cetera, et cetera. Yeah, there's a space, that's a problem. So it's got to be something where it's continuous. Yeah. Okay. Any other questions on this part? The next part I'll go over. Yeah, Aaron.
And then does that change as you change the exposure time?
So yeah, I guess from an optical perspective, the depth should be the same. It's a question of when you deal with it from the dynamics as well as the system, basically signal to noise, whether or not you actually are integrating all from the same depth. So I would think that the longer exposure time gets, the deeper you're probably being able to probe, is my guess. Yeah, this is where Speckle gets very confusing very quickly, because if you look at the you look at the penetration depths of a lot of these wavelengths, they're millimeters. Like they say, even so in a mouse brain going through a cortex 1 millimeter, should be no problem. But the actual depth over which you can collect data, even at a single exposure, basically it's shallow. It tends to be shallower than that, because your signal to noise gets worse and worse as you go deeper and deeper. We've never done that sort of study, and that would actually be kind of a cool study to do, even computationally. But I don't have an answer to that. I guess you could do it experimentally too if you have a phantom where you start moving things deeper, faster flow speeds. I guess you could do that, yeah. Okay. Aaron touched on this part, so I'm gonna I'll kind of just jump to the result. Is if you just change optical properties, what happens? Right? So if I just double the amount of absorption or double the amount of scattering, what happens? I'm not putting a layer on or anything. I'm just, mixing a dye or mixing in more scatterers. You're going to get different correlation times. How different is another question, but optical properties will affect speckle contrast. And so these are experiments Aman Mazar did when he was look at this when he was transitioning to a postdoc here. So these are just intralobate phantoms. I don't remember what the absorber was. So he either varied scattering or varied absorption. And so in those cases, and they change exposure time. If you just look at a single exposure time, you just look at 10. Well, actually, what do you think will happen? So these are liquid phantoms. What do you think will happen if I put in more scatterers? Do you think contrast will increase, decrease, stay the same? Is there a decrease? Why will it decrease? Oh, okay. Yeah. Sorry, I've tried. Maybe the question I asked isn't the question I thought I asked. What did I ask? With what? Okay, with increasing scattering. Okay, okay. That's what. Sorry, I had a brain fart there. Okay. Yeah, so you increase the scattering, you're going to decrease basically your contrast. So you are decreasing the penetration depth, but you're interacting with more scatterers. Scatterers all have this, let's say, the same decorrelation aspects to them. So now this is a pretty big range of scattering change. So it's an 8-fold change, and you get basically pretty small, a modest change in the contrast. With absorption, what do you think would happen if you increase absorption? Will you increase contrast, decrease contrast, or will it stay the same? Increase? Is that what I couldn't hear? Is that what? Why would it increase?
Surface level, right, if there's more absorption, right, and a lot of scatter will be, there'll be more difference between the signal and absorption, a lot of scatter.
But if you have more absorption, what is it doing to your path length? Decreasing your path length. So, and yeah, so basically you increase absorption, you actually increase the contrast. And this is a bigger change. And it's largely because, yeah, you're gating out those longer path length photons. They're getting absorbed, right? So even if you have a lot of photons experiencing a lot of scattering events, if it doesn't survive and come back out, it's gone. And so you're gating out those longer path length photons with increased absorption. So the only ones coming out are the ones that scatter less, on average. Okay. So, okay, I think we just talked about that. So this is just a different form of the correlation diffusion equation. Erin did a great job talking about it. She did actually better than this. But yeah, same thing. We have kind of this dynamic absorption, this dynamic loss term here. We call it dynamic absorption. This is basically Dave Boaz helped us develop this. In the space, he actually did it in the spatial frequency domain. We haven't talked about spatial frequency domain, so I won't. So if you actually take light like this, you actually take the laser light and you structure it. You put it in a sinusoidal pattern. You basically take it, you bounce it off of in this case, this is a liquid crystal on silicon display, reflected, but you use a spatial light modulator as well. Do a sinusoidal pattern illumination. You can model that in the spatial frequency domain, how the light propagates at the different wavelengths and how that affects speckle contrast or just correlation. And so you could also, the simpler thing we do is we just set it to 0 for planar illumination. All these parameters are they're out of David Kucha's original spatial frequency domain imaging paper as well as Aman's paper. In terms of, but all these parameters, these are just optical properties, spatial frequency, and then you have basically boundary conditions that you set. You could forward model this pretty quickly. And so this is Tin's system here, and we can show it to you. I don't think we're bringing it up, but we can show it to you. This is just a combined speckle and spatial frequency domain imaging system, but the speckle is just planar speckle. And then we take the optical properties and measure a spatial frequency domain imaging, and we use that with the to then supply these values to then try to get G1 out of it and then get the contrast out of it. So in this case, we're actually kind of we're not assuming G1 is that it's single exponential. We're actually using absorption scattering properties as well to basically create a shape for the G1 term. Final thing, Monte Carlo. So we've been talking about Monte Carlo. If you have n photons, you run them through, you measure reflectance. You can then determine at different angle. You can measure reflectance in lots of different ways. But basically, that's Monte Carlo. So this is something Carol was instrumental in helping us develop, was this concept of if we try taking into account other things. So you have heat diffusion, you have optical diffusion, heat diffusion, or mass diffusion, heat diffusion. You can also have momentum. You can have a diffusion of momentum. And that's related to actually what Aaron was talking about is basically electric field decorrelation. So we can look at momentum transfer, and we look at that from just direction of the scattering event, and we create a distribution of dimensionless momentum transfer. What does this all mean? Okay. Here's my light, here's my photon going in, bam, goes in a different direction. There's also, and then you can also think about it as, from a momentum perspective, is it imparts momentum to that other marble in this specific case. But basically, we get a redirection of the scattering. It was going, photon was going this direction, and now it's going that direction. So we get a scattering angle. And so each scattering event with a moving scatterer will lead to momentum transfer. Okay, so photon interacts with a moving scatterer. It's going to impart momentum to that scatter, very small, but it's going to impart some momentum to the moving red blood cell or the moving scatterer. And so what we do, and this happened, basically, we're accumulating these phase shifts that occur with each one of these events. And the more phase shifts you get, the more decorrelation of your pattern you get. So what we do, so just thinking about this mechanistically, or not mechanistically, just thinking about this practically, each time the photon scatters, we measure the angle. We already and that happens already in Monte Carlo. We just tabulate it as basically the momentum transfer. And so it scatters 40 times, let's say with moving scatterers, we're going to have 40 different tallies. And we're going to sum it all up. We're going to get some value of y. And we build up, and then we send in the next photon, the next photon, the next photon. Each one of those is just another tick mark in this probability, in this histogram that we generate versus y. So this is the sort of thing that we can generate. Okay? So the idea here is that we basically, with all those interactions, we basically have some photons that had, just a little bit of that buildup, the momentum transfer, and we have some that had a lot, and then we have this distribution here. So this is less decorrelation, and that's going to be more decorrelation. So we're able to take that distribution that we can simulate. This is where we can start going to really complicated geometries. We're going to like multi-layered geometries where some have blood, some don't. And we basically are then able to build up RG1 through simulation. Okay, this is derived from I got it from, or we got it from one of De Bois's papers, and it was basically also published in some other papers. Basically, you get this probability distribution. There's that delta R squared term that Aaron had showed. Basically, the root mean squared distance that the blood cell, basically that the blood cells quote unquote diffuse with a given period of time. K is the wave vector, and so we have all those parameters from the Monte Carlo that we can then basically use to create to create the G1 function itself, and then we can go. So we're not making, sorry, that should be a little G1. We're not making any assumptions on G1. Now we're just taking it, the distribution, we're just plugging it in. And this is what Aaron had talked about. So we can do this and then we just plug it into and we get contrast. So this is one example of a distribution that we simulate. This is sort of the skin. And so, multiple layers. This is actually two different diffusion coefficients. But there's a darker pink and a lighter pink area there. So, skin and then and just different levels of flow, I guess, or vasculature. And so we can then tally up momentum transfer from these different areas. So we can, store this sort of information at different wavelengths. And you just see different wavelengths. The y-axis is changing too, but basically, here we have the light's going deeper, so we basically are having fewer momentum transfer events than it is more superficially for the really short wavelength lasers or light sources. And so we could build this up. We can get reflectance, and this curve you all, I think, have seen or in papers. And we just look at melanin, for instance. So this is one of those things we're interested in was, we know that darker skin is going to have less light come back out. We know that. And that has an impact on multiple things optically. So, in an ideal world, you change the epidermal absorption and nothing changes. But we know that doesn't happen. So speckle contrast, we can simulate now with this. And we do speckle contrast, this is what we see. There's a pretty big difference in melanin content. And yet speckle contrast, especially if you're working in where people typically work at, It's a very small difference. So it's pretty cool. We verified this experimentally with phantoms, with layered phantoms, that this indeed is the case. And we can talk about the why later, but it already goes to show that, you think about PPG, you think about SPG, photoplasmography-based versus speckle-based measurements. There's a lot of advantage potentially to doing speckle-based measurements instead. Yeah, this is just showing, I'll skip that. So yeah, this is just another way of looking at it. And indirectly, there was some work by that LAS company that kind of confirmed this observation. But yeah, basically, signal attenuation is a lot higher with PPG than it would be with SPG. And no, that's not a middle finger goes sticking up. So you can kind of do pulsatile as well. You can try to simulate pulsatile flow. These are measurements, and then we try to simulate pulsatile flow with some assumptions baked in. There's some work from Cody done. Actually, I forgot the reference. If we do comparison of what we measure in vivo versus modeling, you get similar sorts of amplitude differences. This is like with a PPG. So my watch does green PPG, but if we look at green speckle versus near infrared speckle, big difference in the amplitude. So to summarize, at the end, standard LSI, this is the kind of governing set of equations, and a lot of people have used it. A lot of papers reporting on this. Is it perfect? No. Is it useful? Yes. For looking at trying to measure dynamics or measure motion dynamics. Multi-exposure, if you want, I forgot to put temporal here, but you can do temporal, which is pretty simple as well. You can do multi-exposure if you go and just go to multiple exposure times. You can then try to back out the dynamics, the correlation time, with a little bit more involved of an approach. We can use correlation diffusion approximation to try to simulate speckle contrast and also be able to convert measurements that we have. If we measure optical properties and we measure correlation time, we can then or measure speckle contrast. We can actually try to back out then the diffusion coefficient. And then you can just model it, right? You can just basically do simple geometries, more complicated geometries, and you can basically model the momentum transfer from simulation and be able to then try to make some inferences on what's going on inside, with the speckle-based measurements. So, final thoughts. This is my last set of slides here. Is, and this is all opinion. I really think standard LSI is it's really enabling in terms of trying to look at blood flow. There are caveats to it, but it's very simple to implement. The engineering is really I call it the fun part. It's also the challenge, because a lot of these things, especially with miniaturized components and things like that, trying to get things into wearables, into smaller devices, it's fun, and it's potentially very enabling. But it's also some of the electronics and everything can get pretty involved. But it can be very low cost, as we had said earlier. I think there's some really cool, powerful twists, and so this is work that that Anna's going to start working on, basically using SCOS for blood pressure, or she's working on it now. So Ariane Garrett was, did she graduate, or is she still? Oh, awesome. She's waiting for you. Okay. All right. I don't know if she remembers me, but tell her I congratulate her. Okay, I congratulate her. So yeah, actually, they have a newer paper, so I should update that reference. But it's work between Anna's PI, Darren Robler, who will be here. I thought he might be here today, but he'll be here tomorrow for sure. And David Boaz at BU. There's some person here that's basically with the SPG based techniques. Kiki's work. This is a great paper. And so I think just taking this sort of technology into pretty to try to do pretty challenging clinical translation, I think it's a very enabling technology for that. High speed, so taking, like some of the stuff that Aaron was talking about, with Speckle, you're not going to go at the same speeds as DCS, but we have a camera that can go tens of thousands of frames per second, And so you can start trying to measure the correlation time using that sort of technique. This is work also that was originally from BU. And so it's more a fundamental type of system. And then modeling, I think, is just a great way to kind of test out things with Speckle and see where you're sensitive to. And maybe could try to address the question that Aaron had posed about depth. But those are the sorts of, that's a playground that you could use to try to look at different parameters and see what the impact ultimately is. So with that, thank you. And I'll take any questions. Yeah, Aaron. Yeah. Yeah.
Make assumptions of a homogeneous model or, set, but the industry show is really not homogeneous, right? There's like big bloods.
Oh yeah, sure.